Hello. Um, just the usual. Is my microphone working? Can everyone hear me out there? I'll just wait till the stream catches up. I always love when I log on for a live stream and the live stream's already got likes on it, and I'm just like, hey, don't actually have to do any work to get likes, just getting likes. I don't know if it's just the same 2 or 3 people who are like always liking the video before it actually happens. Um, but I guess it's kind of fun that, in these times with a whole bunch of us locked up in our homes and things like that because we don't really want to um, spread the whole pandemic further than it's already gone. People are still enjoying themselves and just having at least a little bit of fun with what you're doing. Oh wow, the likes just jumped up. Oh, okay. So this actually does work. See, I'm learning how to be like a pro streamer. That you just like keep telling people to like and subscribe and stuff like that. Because yesterday I mentioned subscribing as a joke, because it's really not super important whether you subscribe or not. Because I'm going to put all the links on WebCMS, which is like the official portal to the course. But then a whole bunch of people subscribed when I mentioned it, and then I mentioned likes today, and then we've got a whole bunch of people liking it just for fun. So Tom's saying everybody remove your likes. Ethan asks for more of chicken. So there's only one door into this room that I'm in, and the door is in the background there. And so, to be respectful of my partner who might be moving around the apartment as well, I leave the door shut. So whether chicken appears in a lecture or not is based on whether she happens to be in this room when I shut the door. And I know that today she's not in this room. But maybe in the break I will try to get her to come into this room when I've got the camera off, and she might make a cameo later on today. Julian's asking for more memes. There's at least one meme. Oh my! Everyone's so sad. The chicken's not here. There's at least one meme today. It's a meme I used before, but I like the meme so much that it's going to happen. Actually, there's more than one meme today. Okay. Milkshake gamer. Chicken's like Stanley, so chicken turns up at random moments. Okay, let's launch into it. So, what were we talking about yesterday? So yesterday we went through a sort of next level in our thinking about memory. So during the whole course, I've been talking a fair bit about how memory works. So even from the very beginning, when I said what a variable is, I was trying to point out that a variable was a piece of memory, so actual bits that can be switched on or off to ones and zeros, and an integer, for example, is 32 bits, a double 64 bits. And they're sitting on our computer's memory somewhere. So the same kind of thing that you get told about when you purchase a computer, this thing's got 16 gigabytes of RAM. That's part of the memory system of the computer, and that's the main memory that we use the most. Our variables will physically be sitting on these chips somewhere and being represented. Now, as of yesterday, we started looking at not just the memory that's sort of handled automatically by C, which is stuff like we create variables, when the curly brackets finish, the variables go away. Now we have the ability to grab a piece of memory that's been assigned to our program. So our program, as we saw yesterday when I blew it out, had about 8 gigabytes of memory as its maximum possible that it could use, and we could put things in those 8 gigabytes of memory. So we can assign space for variables. Very often we'll be doing this with structs, and we had an example of that as well. This allows us to create things with our code that are persistent beyond the function that created them. So when we want to, we can use a function to make something, and instead of when the function ending, that thing disappearing, if we use malloc, memory allocation function, it will then be there for use for us for the entire program until we say, okay, we're done with this, and we call free, which is the thing that lets it go again. People are threatening to unsubscribe if the cat doesn't appear. Yeah, otherwise everyone's saying hi. Hi everyone, how's it going? We also had a quick look at multi-file projects. And the multi-file project was starting with the idea that we can have our code separated in multiple files. And this isn't just we have so much code we want to split it into multiple files so it's easier to read. This was actually functionally useful as well, where using header files and C files, we can include a header file in something like our main. We can actually include header files in other files as well. And by doing so, we will see what functions have been implemented in the C file. But as you saw, we used a type def to say that we could only see a pointer to the structs that were in the C file, but the main file never knew what the struct was. So this meant the only way that the code that we wrote in our main file had access to any of the data that was in the struct was that it was calling the functions that were in the H file. So it could never actually look into the struct itself because it didn't know what was inside the struct. Even though the C file has it all defined, it never looked at it. So that way what we can do is we can say to whoever's programming in the C file, yes, there's some data. Yes, you can access it, but only through these functions, which means the data is sort of protected from anyone accidentally accessing it the wrong way. And so anytime anyone wants access to the data, they're going to use the functions provided. We're going to look at this a bit more, not necessarily today. Next week, we're definitely going to be looking at this a bit more. You're definitely going to be looking at this a bit more next week because there's going to be an assignment released with information about that. So next week, we will be doing our 2 normal lectures. I mean, usually this would be more different than this. So usually we would be having the 2 normal lectures in the lecture theatre and a live stream as well. But all of our lectures are kind of live streamed now. So next week, I'll just kind of be giving 3 lectures. In a sense, I'll do one later in the week, I think, that takes you through the assignment and gives you sort of an explanation on what the assignment is doing. I mentioned in the stream where I was talking about the course layout and things that given the fact that the assignment was going to take more time than the exam, and the exam wasn't as much a hard line true assessment of exactly how you're going in the course. Like the exam now gives you some time to look up resources and things like that. So it's slightly different than full-on testing your knowledge and being this kind of gate that we put on whether people can complete the course or not. We're going to be shifting some of the marks into assignment 2 rather than having the massive bulk of the marks in the exam. The exam's still going to be worth more than the assignment, but there's going to be a little shift there. I'll have that finalized before the assignment is released. The planned release for us is going to be Sunday, I think. It'll be the same kind of release as last time. I think we're pretty ready for a Sunday release. Let's see if... yeah. I think... Mega Abominator is asking a question, and Tom's answered that. For the moment, yes. Someone wants to know where I get my T-shirt. Should I get like endorsements from clothing companies and things for my cool pop culture T-shirts? This one was from Uniqlo, actually. Anyway, let's go on to actual content that we're looking at today. So today we're covering 2 things. One of them is a little bit quicker than the other, which is command line arguments. So every function that we're using, you could call its inputs arguments. So sometimes they're called that, definitely. The other thing that we've seen happen when we use something like DCC, so note that every time we run DCC, we type in a name for a file, we type in a -o, and a name for an output file. We don't always have to type in -o, like it'll just give you a generic output file if you don't type in -o. But we have the program name, DCC, and then a bunch of other things. When we're running our own C programs, we do // and the name of the program. You can actually put more words after that. And if you write your C program in a certain way, the words, numbers, whatever you put after you run the program can actually be pulled into the program and used. So that's one way that we can run a program with really specific setup. So we can run it with the idea that we're going to have certain information to start the program, and then after that we work on other things. So up until now, everything we've done, we've just said, okay, after you start running the program, scan F in a few things, or F gets whatever, a few things to do the setup, and then launch into the program itself. So we're teaching you a way today that you could, if you wanted to, start a program with some other information, and that could be all of your setup. So that's what we call command line arguments. So they're actually typed in the command line at the same time that the name of the program is typed in. I'll show you examples of that, how that works. The other thing we're starting today, and we're only starting this today because this is a big topic. This topic is going to stretch through probably at least half of today's lecture, and it's going to go on for pretty much, I think, the whole of next week. We'll be doing one kind of pretty big worked example of all the kinds of things we can do with this thing called linked lists. Linked lists are the sort of pinnacle of what we can do with the coding we've learned in COMP1511. So a linked list is something that uses a structure to define an element of a list, different from how an array was just had an elements in its sort of list of items, and they were just variables. This time, every element is a structure, although you can do an array of structs as well. So the difference you'll see as it goes along. It uses memory allocation, it uses pointers, and it uses structs. So what linked lists are now is us tying together everything that we've learned so far. So everything that we've learned about how to aim at things in memory, everything we've learned about how to chain together multiple items into a struct, and also using memory allocation so we can create these things and have them last longer than the functions that created them. All of this stuff is going to build us together into this kind of conglomeration of everything. Or like, you know, stitching together dead bodies into a zombie of things. I just thought that because someone was talking about Abominator there. It just made me think of abominations and stuff. Tom's saying I should wear CSE sock merch. I will probably wear CSE sock merch at some point. I was looking to see when they finish their new hoodie design for this year, and I'll get one of them. Although I don't know if this term will even get cold enough for me to need to do that. I don't know if anyone noticed, but I wore a CSE review t-shirt sometime in one of the previous streams. So yes, there'll be plenty of merch. AA is asking, will the exam be harder than usual since we're given more time to complete? Tom's answering that there's be loads of info later. If you want a really, really simple answer, actually there's no simple answer to that. So yes, I could say the exam is harder, but it's the fact that it's an open book exam makes it not harder. So I don't know whether in the end it will be harder or not. One thing I can say about the exam, which is interesting, sorry, the question here was, is the exam going to be harder because it's open book and 24 hours and stuff like that? The main difference between this and the normal exam you would have just your brain. Like, we don't give you anything else, we don't give you Google, we don't give you access to the lecture slides or anything like that. So it's like, what went into your head? We're testing what went into your head, which is a good thing to test when you're teaching students, right? If I'm teaching you things, I want to know what you've actually picked up and what you've remembered. The exam this term will be slightly different. It won't be what you've remembered. It'll be how resourceful you are in a day's worth of programming. So whether you know how to look stuff up online maybe, or whether you know how to go back through the lecture slides and take what you need from the lecture slides in order to answer questions and things. In a certain regard, that's actually more realistic, because I don't program without Google. So usually when I'm programming, I have one monitor that has my code editors and stuff like that, and another monitor that has a Chrome window open, like a browser window open, that I can just go search things if I need to. So if there's a weird idea that I haven't done very often, then I'll go look it up to make sure I'm doing it correctly. Even stuff in COMP1511 sometimes I will look up, you know, like even if I'm a lecturer in this, it doesn't mean I've memorized everything in the course. So you will be tested in what I would consider to potentially be a more professional environment than the getting locked in a room with no Google and being asked to write code. So it's an interesting thing. Depending on how it goes, I might think about the idea of exams having a little bit more open information in them. But it's hard because the majority of professional programmers would just ace our exam very easily, but I need our exam to be at the level where it makes sense to people who have only done programming for 10 weeks, rather than at the level of people who have been programming for, like, you know, I don't know, say 3-4 years or more. If you've been programming for 3 or 4 years or more, the stuff that we're doing now is relatively simple. Sure, some of the fundamentals not everyone keeps track of, some people forget it, but most people who are professional programmers should be able to sit our exam without a great deal of difficulty. Which means the resources they write about online and the questions that they can answer online, that kind of thing, would make parts of our exam trivial. Whereas I still want those parts of the exam to be meaningful to those of us who are still learning and are still picking things up as we go. Okay, so little aside talking about the exam there. Let's talk about the 24 hours. Please don't work for a whole 24 hours. You're actually better off if you work for a bit and you sleep for a bit and you work for a bit than you are if you try to stay up for 24 hours. I think if you stayed up for 24 hours doing our take-home exam, you're more likely to just sort of ruin something that you got right first time by continuing to work on something while you're in a lack of sleep situation. But you'll see. Oh, Finley's asking if there'll be a recommended time to complete it. I think Tom's fending that one off for us, but because I haven't thought of that myself actually. But I would recommend something much less than 24 hours. The reason we have 24 hours is that a lot of people in the course are sleeping at different times. That's not just because you're locked in your house and you've gone full cabin fever and you're sleeping through the day. We have a lot of people who, due to the COVID-19 issues, have had to leave Australia and go to other countries. So this isn't something where we would just say do it in daytime Sydney. Because if I said do this daytime Sydney, and someone had gone back to Europe, for example, then they would start after dinner and be expected to hand this thing in before breakfast, and that's just mean. So the 24-hour window is more so that every single person doing the exam gets the same number of awake hours to do the exam. It's not a recommendation that you should spend 24 hours working on it. Alright, I'm going to let Tom answer a lot of the questions in chat, because chat's pretty active at the moment, and I'll get on to what we are doing today. So first thing that we're doing is the command line argument. So quick recap of characters and strings, because we did this last week and I didn't really recap this part of it. So a character represents a letter. A character is actually storing a number value, which happens to be an ASCII code. And so very often we'll use ints to represent characters. We will usually only use the actual char variable type when we're making strings, because as you saw, when we were running functions like getChar might be able to give us a negative number, and the char 8 bits only stores a value between 0 and 255. So it was unable to store the negative value that getChar was telling us. So when we're reading integers in, we'll often when we're reading characters in, we will use integers to represent them. And then if we put them into strings, then we would convert them into the actual character. So, and that usually happens automatically. I'm going to show you something about converting strings to strings to numbers though, which is an interesting thing. I think we're going to do that today if I remember correctly. So when we use characters in an array, they're referred to as strings, and they will be finished with a null terminator, which is just another character. So it just takes up another 8 bits somewhere in the array, and it says everything up until this point, up until we hit the null terminator, are the characters that are intended to be in the string. Everything after that is memory that we have available for the string, but we're not currently using. And that way we can have a string that can represent lots of different lengths of words or sentences, or just strings of characters. That's why they call it strings. So I guess the interesting thing is, like, you know, when you've got memory for a word, you never really know exactly how long that word's going to be, and you don't always expect to be using exactly all of the memory. As opposed to other arrays, like something like your Minesweeper grid, you expect your Minesweeper grid to always be full. But if we were using a two-dimensional array of words, like yesterday when I showed you that Batman example, the two-dimensional array of characters, which was just an array of strings, which was the powers, all of those were different lengths. So ninjutsu was a certain length, and the gravelly Christian Bale voice was much longer. But those arrays were large enough to fit any of those, and they're always finished with a null terminator. So the strings look a little bit like this. We have some ways, if we want to, of initializing strings. And the shorthand like this, with the double quotes, is something that we've seen a fair bit. So the double quotes is something we've been using in printf and scanf, and that would allow us to initialize a string immediately, like this. If we're not initializing the string and we just want to set a string to a value, we can't necessarily just set a value using the double quotes, because that's like trying to say, make this one array equal to this other array. And what we'd have to do, the same way we would do with arrays, is we'd copy it letter by letter. If you need some easy ways around that, the string.h library has some functions you can use for that kind of thing. And as Tom's saying, if you're working with text, character arrays are things that you should use nearly all of the time with a null terminator. Actually, wondering about this one here. See, as I was saying, I don't always remember everything in C, because I never use this format. I just use this format because it's easier. Like, look how much less I have to type out. I'm not sure if this one actually will give you a null terminator or not. This might actually only give you the letters and might not terminate properly. You can always try this out, see what happens. Because a string without a null terminator is going to do some very strange things. Yeah, Tom's saying he doesn't think it will. In fact, I'm going to just, change these slides here, because I think that you need to do this to make that one do it. And I'll just change that back to that. There we go. Yeah, because if you're explicitly putting single characters in, it won't just freely give you the null terminator. You'll actually have to put it in yourself. As I said, I don't actually remember this because I don't use this format for strings, because this format's so much easier. Okay, so knowing that we have characters and strings, we're going to now work with command line arguments. So sometimes we would like to give information to our program when we're running it, and this is at what is called the command line. The command line is this line here, where I type commands in. So if I type in ls, that's a command that goes into the command line. I press enter and something happens. So this is me setting up the stuff for today and just copying the code in. All of these are commands that are typed in at what's called the command line. So arguments at the command line are extra things that we can add in after we run our program. So I can say program and then extra information 1, 2, 3. All of this stuff will get put into our code. So all of this stuff is going to go into our program as a set of strings. So each one of these is going to be separated by spaces and become its own string that my program can use. So all of this information is going to get made into an array of strings inside my program, and then I'm going to be able to read everything that was typed in the terminal when the program was created. So someone was asking for memes. Let me just move my face out of the way of the meme. There's nowhere on this slide where my face is going to fit. Alright, I'm going to go up to the top left. So main functions that accept arguments are written slightly different from other functions. So up until now, our int main has always had void in its inputs. And void, as we learnt when we were working with functions, was a word that meant that there was, for functions, a void function was a function with no output. argc is argument count, which is going to tell us exactly how many things were typed in on the command line. One thing to remember is the exact number of things that were typed in the command line includes the first word on the command line, which is the name of the program itself. So your /program name is always going to be the first thing, and then the second thing is going to be whatever you type in after that, third thing, etc. So this will count how many things were typed in, and it will also do this. argv is, hang on a second. Oops. I just saw this and I just wanted this to be lined up better. We put the star on the variable even though character star is the character pointer is the variable type. We still put it here because it just reminds us that it's a pointer in the actual variable itself. So this is a pointer to a character array, or actually a better way of thinking about this is an array of character pointers. So if I have an array of character pointers, that means that each character pointer is pointing at a character somewhere, and I have an array of them. What this actually means is it's an array of strings. So the character pointer could be considered a string because it's a pointer to the start of the string, and then the end of the string is wherever we hit a null terminator. So we've got an array of character pointers which says that everything in my array is the start of a set of characters, i.e. a string, and I have an array of them. Exactly how many of them are going to be in there is the argument count. So as I was saying with arrays, like we talked a bit about these yesterday when we're talking about the length of the arrays. You don't know how many character pointers are in my array. You don't know how many strings are in argv, except you are told how many strings are in argv by this argc. So that means we can use this safely. Alright. Was everyone getting lag then? Or I just got a little bit of lag? Ooh, a lot of people got lag for a second there. Hopefully it's okay. I hope everyone at least heard what I was saying there, because the slide didn't really change then. Tyler's asking you about the / in the first string of the argv. Yeah, you're going to pick up the / as well. So exactly everything that is written on the command line will go in. We'll show you that. I'll show you an example of that in a second. Okay, let's go to the next slide, and I'll move my face out of the way again. So here is an example of use of arguments. So while we were talking about command line arguments, I thought I'd make a program that actually has an internet argument with you. So what you do is when you're running this program, you type in the name of the program, and then you type in some text afterwards. And no matter what you say, the program will always say, well, actually, this program says there's no such thing as, and then it will loop through here in this while loop. It'll loop through all of the arguments, starting from 1. Rather than starting from 0, it'll start from 1, because it's already used 0 as the name of the program, and then it'll print out everything that you said. But no matter what you say, it'll tell you that there's no such thing as what you said. So just a fun thing. It's just basically like reading the comments section on anything on the internet. So You can see I've used fputs here. Fputs is going to allow me to just write out an entire string in one go. So this is going to loop through all of the strings in argv here, print them to standard out, and put a space in between them. So hopefully what I'm going to get out of this is my argument program is going to spit out everything that I said, except it's going to say there's no such thing as what I said. Let's go have a quick look at that. Okay. Arguments. All right, here it is. I just want to move this actually because it's slightly annoying me that the while loop, the sort of structure of the while loop there, I want to keep it all together so I remember what's happening, because starting at 1 is something we don't usually do, so I need to remember that we're doing that. The reason I'm starting with 1 is I've already used 0 here, so I didn't need to start at 0 because I had a specific purpose for 0, and then I started at 1 and all the other arguments are there. So what's going to happen in my main here is I'm going to run it, I'm going to set a number of arguments, and those arguments are going to get stored here as strings. And the program is just going to take whatever arguments I typed in, it's going to print out the name of the program there, and then it's going to loop through with spaces in between them, print out all the words that I have that I've typed in the command line. So let's compile this and see how we go. Well, I should save it first. Okay. DCC arguments.c output, we're just going to call it argument. So if I run /argument, chicken is a great cat. So I am making a claim that my cat is great because I love my cat. It's not in here at the moment, but anyway. When I press enter, all of the words that I typed in the command line get passed into my main function here, and they get stored in this array called argv, which means I have access to it and I know how big it is because of argc, and then my program is going to print out a bunch of this stuff. So let's see what my program does. Well, actually, .argument, which is the name of the program there, so you can see the first argument, says there's no such thing as chicken is a great cat, which you can see it's taken the words, each one of the words, and it's printed them back out. So I could run this multiple times with lots of things. We had fun writing Minesweeper. See, I'm putting these positive comments in here and all this niceness, but my program is still arguing with me. There's no such thing as we had fun. It's also not making a lot of sense. Maybe I should have put some statements in that were different. But the demonstration, as you can see here, shows you that we can take any information that was typed in while the program was being run, so the / line from the command line, and we can get that information and use it. Bit of conversation happening in there. Sean, yeah, this is just a variable, and as you can see, these variables are built for us from the information I typed in at the command line. So argc will be exactly the number of space-separated words that I have put in the command line, and here will be the exact strings of them. Calvin's asking what the printf of the space does. When I'm doing the fputs, I'm printing out the raw strings. So the spaces don't get pulled into the argv. So each of the argv is just the letters with no spaces. So the printf here with the spaces, just putting spaces in between them, so that when we read it out, they don't, when it's printed out here, they don't end up right next to each other. Pelong Lee is saying command line arguments act as the input to main. Yeah, that's basically what it is. We can have the main function now with inputs, except the main function is not called by another function, so we can't say main open brackets and then put inputs in. But with this particular layout, C is able to take in whatever we typed in the command line here, that will then be chopped up into a set of strings and then put into our main function. I'm just going to make sure that my face is not covering up any of the code today. Let's move that over a bit. Okay, good. Okay, lots of conversation happening in there. Michael's in there answering things. I'm just going to assume that Michael's got that one covered. Thanks, Mike. It's alright, I should get back to lecturing. Okay, so this example just shows us that we can grab the strings that were put in as input, and then we can use them in some way. So this is a really simple example because the only way I've used them is just to print them straight back out. The other thing to think about is the arguments in the argv that are passed into our main function are always strings. So in a sense, what we're getting is the raw information that someone has typed in, nothing more than that. So we can read the strings in, but maybe we want to process these in some way, like use them as numbers. So it's reasonable to think that I might want to run a program that has numbers as its command line input. There are some library functions we can use to help us with this. If we wanted to, we could find the numerical value of any string, so long as we knew that it was supposed to be a number that was typed in. We could do this purely by program. So knowing that the numbers are in order, and that 0 is lower ASCII value than 9, for example, we could minus the character 0 from a number and then switch things around and stuff like that. It's quite involved, though, to convert a string to a number, because you'd have to first figure out how many digits there are, and then you have to do some manipulation on those digits when you read a series of them to figure out exactly what number that is. So a lot of the time when we're doing stuff like this, we just use standard library functions to do it for us. So there's one called stir2l. It's like, again, one of those like unnecessarily compressed function names, and it's in the standard library, and it means string to long integer. There's several of these available. There's actually multiple ways you can convert characters and strings to numbers. But this is one that I think is reasonably easy to use, that is made to grab a string and turn it into a number. So stir2l is something, and like this is again something that I would often look up because I don't always remember exactly what the inputs are for it. It's in the standard library, and we can use this to convert number input, string input that's intended to be numbers into actual integer variables. So code looks a bit like this. This time we're including not just standard input output, but we're including the standard library as well. This function here, all it does is it takes all the numbers that were typed in the command line, and it converts them all into numbers, then adds them all up, and then prints out the total. So I'm using the string to long here, and it's going to take in a string, and I think this is a pointer to the string itself. I think it's a pointer to the string where the number's finished off. I don't actually remember because I use it as null most of the time, but I think it's something where we can use the pointer to store something. Don't worry, you can just leave this part as null. And here is a 10. The 10 here is me saying I would like to read in whatever was written in the command line as if it was a base 10 number. So assuming that the digits that someone typed in there were the same digits that we use. So 0 through to 9, meaning the same kind of numbers that we use. If I wanted to, I could say, put a 16 in here and say, I expected the number that someone was going to type in was going to be a hexadecimal number, and so I'm going to convert it into a hexadecimal number. Or I was expecting it to be a binary, I could have a 2 there. But most of the time when we're reading from a human's going to write stuff in base 10, because base 10 is a numbering system we use most of the time. So what this function here is going to do is it's going to read in one of the arguments, expecting it to be a number, so we're not doing any error checking here, expecting it to be a number, and this function is going to convert it into an integer. And so this whole thing is going to end up becoming an integer value, which we are then going to add to our total. So our total with this accumulator here, do you remember these, the plus equals? This is going to just keep adding the values that are created by this to the total. So let's hop back across to the code and have a quick look at that one. What did I call this one? Adder. Francis is asking about what's null and 10. Oh, there's actually quite a few questions coming up here. I think Michael's answering most of them. Alright, a lot of people are getting their answers. Okay. Francis, I don't think I've answered yours yet. String to long is a specific function. What we can actually do here is I can look up the manual for this and see what it gives me. Okay, string to long, string to other things, convert a string to a long integer. Hash include standard lib.h. String to long is the one we're using here. Pointer here, character pointer, end pointer, base. I think string to long function converts the initial part of the string in nptr, which is this one, to a long integer value according to the given base. The bases here, they say must be between 2 and 36 inclusive, because maybe those are the only numbering systems they can use. Or special value 0, I don't even know what the 0 does. String may begin with an arbitrary amount of white space, so it doesn't have to have numbers. You can have a positive or negative. It can include a 0x. String is converted. If end pointer is not null, string to long stores the address of the first invalid character in end pointer. So if we want to, we could give it a pointer to another string somewhere that we're using. And then what it would do, we'd give it a pointer. And it would be able to give us the location that the numbers finished in a particular string. So let's say I had a string that had numbers at the beginning and letters afterwards. This function would process the numbers, and then it would find the first letter that wasn't a number and go, all right, I'm going to give you that location and say, this is where I finished reading. So I read these numbers and then these letters started appearing, so I stopped. I stopped reading numbers because that's where I got to. So if you want to, you can use that to figure out whether the number was read in or not, or if you have a string that has combinations of numbers and letters and you want to strip the numbers off the front, in a sense, and use them for something, then you can use those pointers. In general, I'm not going to use those. And in 1511, we're definitely not going to bother with any of that. We're just going to leave this as null because we're not going to use it, and we're going to think of it this way. Convert this string to a number in this base, and we'll forget about the null. Like, you can happily forget about the null. We're not going to use that in most circumstances. But I thought I should at least say what it is, just in case. Okay, so going back over what this code does. It starts with nothing in its total, so 0 for its total, and then it loops through all of the arguments, not including the program name. So again, we're starting from 1, and we're looping through here, I++, until the end of the array. And for each element of the array, we're converting it from a base 10 number into an integer. So this converts into an integer value that we can use, add that to the total, and we should be able to print out the total. So Sean asking about searching the manual. The manual is usually just, I'm going to quit out there, is actually just the command man, M-A-N. That actually runs a program in Linux that has access to all of the manual pages for a lot of things. And so C is included in that. The only thing you have to be careful of is not everything in C is named uniquely. So sometimes we would use man there, and we'd get something that's not actually a C language reference. It's a reference for something else in Linux. So sometimes if you see something and it doesn't have any mention of C or C or H files that it's using, or functions and things like that, it might mean it's from somewhere else. So just be a little bit careful with that. You can always Google this stuff as well if the man page doesn't get you something. Alright, bit of chat going on there, but I'm going to keep going. Okay, so if I was to run this, adder.c, and the output is adder, I have a program where I can do /adder. If I just run that, I should get total 0. Yeah. But if I give it some command line arguments, so I've just put some numbers in here, and I run this, each of these numbers is going to go into the program as a string. So it's a string with a single character in it, each one of these. Oh, actually, there's a large one there as well. Each of these is a string, so there's 3 single letter strings and there's a 3-letter string. These are not actually numbers until they've gone through this function. So this function is just something that converts the numbers that we've typed in as strings into actual integers, because they're different things. If you look up the ASCII values for the digits, they're not actually the same value as the digits themselves. And also, this one here is 3 separate characters. So the only relation it has to a number is that we think it represents a number. So because we think it represents a number, we need to then ask the computer to convert it into a number in the type of numbering system that we think we're in. So we think we're in a base 10 numbering system here, and we ask the computer to convert that 4, then 5, then 6 characters into 456. And then it gets that 456 value, and then we use it here to add to the total. So let me run this. Total is 462, so it's taken the number values of each of these strings, converted them into integer values, and then had them add together into this total. Yeah, I wouldn't worry too much about the null. The null is just something that string to lol can use, and so we could give it a pointer and it would tell us where it finished reading, so where in memory it was when it finished reading the number. But since we don't mind where it finished, because we're reading the entire string here, we're going to put a null in there. Everything that we're going to do so far in this course, whenever we're converting strings to numbers like this, we're just going to use null. Okay, so that's the command line arguments. You'll probably want a little bit of practice with this to get the idea of how this works. So basically, the idea that we're getting at here is we now have a way of taking information from the actual line that's typed in when the program is run. That information will be put into an array of strings, which means that we can access by index each one of the strings that was typed in, and we know exactly how many of them there are because we have an argument count here. I've shown you ways to just use them as words, as strings, as well as a function that can convert a string of digits into a number. Sometimes we're going to want to check that something's a number before we do this, but a lot of the time we're just going to use it as is. I mean, a lot of what we're doing in this course, we don't do that much error checking on stuff like input, because it's really quite complex sometimes, because you've got to check for a lot of different things. So a lot of the time we will just sort of give you the right style of input and have you working on the more important things, like how do we use the underlying data structures like arrays and linked lists, which is coming up next. Okay. I'm going to talk a little bit before we go to the break. The question there was, could we use total plus plus for the plus equals? So plus equals here is not plus plus. Plus equals is add this number to this number. So plus equals says take whatever value this was and add it to the total. So the total starts at 0, and if I have a 1 here, the total becomes 1. So then if the total is 1 and I have a 2 here, the 2 gets added to the 1, the total becomes 3, etc. That kind of thing. So this plus equals is something that just sort of accumulates value as we go along. It's just a shorthand. If I wanted to, I could have done this. So this line is the same as this line. They will do the same thing. I was using the plus equals to just sort of remind you a bit, because I've shown this once before, but I didn't really go into too much detail about it then. So this is the, like, these two are equivalent lines of code. I'm going to get rid of that one so that that program will still run. Okay. So now I want to talk to you about linked lists. And I'm going to start by talking about a specific kind of structure. And this is a new one. This is one we haven't seen before because we have not had any what I would call self-referential structures before. So we haven't had a structure that refers to a structure of the same type. Hyundong Xiu is asking about if we typed in letters into adder. I'm not sure whether the letters will get ignored or not in that situation. I think that they will get ignored, but I'm not 100% sure. Anyway, I'll let you discuss. Actually, Hyundong, I think that's an interesting thing, that you could download the code that I've written for adder, type in other types of input and see what it does with it. I'm hoping that it will just reject them, but I don't actually know because I haven't tested that recently with string to long and seen what it does. Okay, I'm going to start a new topic now. So I have a structure. A structure, as I've said, can have any variables in it. So I have a structure here called a node. The node contains some information, which I'm calling data. So for the moment, I've just got one variable in here called data. But as we know, a struct can contain more things. So I could have many things in this struct if I wanted to. In the same way that the element benders had stuff in them, the K-pop artists had the information in them. Yesterday, the stuff we did with the person had their name and their superpowers and stuff. So there's lots of things that we could store in a struct. The key thing that's really interesting about this struct is it contains a pointer to another struct that is the same type as itself, which means what I'm saying now is I can have a node which is a struct that has some information in it. For the moment, I'm just carrying an integer as my information, but I could have more information in there. Some people call that the payload as well, as in something that's been carried around. But the key thing that holds this thing together, which makes it interesting, is it points to another node. So I have one node with its number in it, and I have a pointer, and I have another node with its number in it. Which means what I could do is I could chain these things together. So this is a picture of what a linked list looks like. So each of these nodes are struct node. So this is a variable type that I've created for my purpose here for this linked list. What it will do is it will sit in memory like this structure. So it's a node. It has a next pointer, which points to something else, which is of the type node, and it has some data in it. So for the moment, I was just using an integer, but what I can do is I can have the next node pointing at another node. And then that next node can then point at another node, and each one's carrying their own data, and the next points at another node. The other thing that we're going to do to make sure that we can use this thing is we have a pointer to the first node, so we're always going to know where our first node is so that we can work with it. Otherwise, we won't know where our chain of nodes are. But the cool thing about a linked list is we only need a pointer to the first node to get access to all of them, because each one tells us which one is next in the list. So we could have these things all over the place in memory, and each one just has a pointer to one of the others, and we can still access it. The last thing that we're going to have to tell us we're at the end of the list, this is a little bit like that null terminator on the string, is if our next pointer points to null, it means that I here am the last element of the list. So now we're building up a new data structure that has structs and pointers in it and allows us to carry multiple elements of information here and link them together by pointers to each other. There's a lot of questions here about what's going on, about what a node is and how these pointers work. So the node is something that we've created. Struct node is the same as like struct person that I created, or struct bender, or did I have a struct for superheroes? I didn't. I had a struct for a performer. I can't remember what I called that. Anyway, I think it was rapper. Anyway, so the node is a structure that we create. Then in here, we have a pointer, struct node pointer. So remember that all of this together up to the star is the variable type. And the variable type is a pointer to another node, which means that somewhere out there, we're expecting there to potentially be another node that we can aim at from inside this node. So one of the fields inside this node points at another node, and then we've got some data in here, which is the whatever we're storing, the information we're storing. So there's two kinds of things. One is the architecture of this data structure with all the stuff in it, and the other thing is what data is actually being held in there. And so looking at this visually, each one of these nodes has in memory its own data as well as a pointer to another node, which means if I'm in one node and I say, okay, look at my data, now I would like to follow the next pointer to another node. I get to this node and I can look at its data and I can follow its next pointer to the other node. So putting a pointer inside the struct to another copy of that struct means that I can put a whole bunch of these in memory and have them chaining along each other like that. Right. Cool. Okay, I think people are getting to the idea of how this works. Michael Ruffle is saying, wouldn't it be possible to have a series of nodes that go in a cycle? Yes, it would. So if this next pointer here pointed at this node, and this next pointer pointed at this node, I could potentially have the idea that things would go back and forth. So I could follow the next here, follow the next and go back, follow the next there. And yes, I would potentially get stuck in an infinite loop like that. We're not going to be setting up our linked lists like that. We're going to be setting up our linked lists in a chain that only goes in one direction, and it starts from a pointer to the first node that we establish is going to be the start of the list, and it ends in a pointer to null to say that I'm finished. And if I've seen this pointer, it means I've gone through all of the nodes, because I followed the chain all the way through to the end. So this is a linked list, and it is different from an array. So an array is a series of identical variables. Sorry, I shouldn't say identical. It's a series of variables of the same type. So our very first array that we used was an array of integers. In Minesweeper, we saw an array of arrays. We've seen arrays of structs. So I've showed arrays of structs before. You can always go back and look at the videos if you want to look at detailed information. You want to slow them down, freeze frame, look at the code and stuff like that can be useful. The arrays were always one block of memory, so one full block of memory, and each element was directly after each other in that block of memory. Linked lists are not one block of memory, they're just scattered anywhere in memory, and the pointers tell us to how to find the next ones. One of the interesting things about that is we have a different way of working with them. So if I have an array, let's say the numbers 1, 2, 3, 4, 5, and I say I want to remove 3. So I want my array to read 1, 2, 4, 5. I want to remove 3 entirely. It's really hard to do that because all I can do is change the value of 3, but I can't change the fact that it is a chunk of memory that's in the middle of my array. So 1, 2 are on one side and 4 and 5 are on the other. If I wanted to squish them together, I would have to maybe make a new array that was one shorter and put stuff in it, and then that would be a fair bit of work. With a linked list, it's actually really easy for me to just remove an item from the list and have the pointers just skip it, you know? And I can insert things partway into a list as well, just as easily by putting something in between. It doesn't physically go in between them, it's just off somewhere in space, and we just change where our pointers aim. And if we change where our pointers aim, we can significantly alter the structure of the list in a way that we couldn't do with arrays. The other thing that's interesting about a linked list is each node in this list is going to be allocated individually. So every time that we make a node, it gets its own memory made somewhere in our memory, and it gets linked up into the list with these pointers. An array will always be one fixed chunk of memory with a certain number of elements in it. So you can't just tack things onto the end of an array because you don't know if the memory there is being used or not. With a linked list, we can grab memory from anywhere and just go, all right, just change this pointer to aim at another node. And so that way we can just add things to a list. We don't need to know how long it is. We don't need to arbitrarily have a large thing. We can have any size linked list that we want. So this is why we use something like a linked list, because it gives us a very different capability than an array. It's slightly less efficient because it needs to carry these pointers. It might be in different places in memory, but we're not too worried about efficiency. Especially in 1511, we're not worried about efficiency at all. But even in other cases, we're not too worried about this with linked lists because they're so useful. Because if I can add or remove elements from partway through the list, if I don't have to worry about how long the list is, it makes it really nice for us to be able to do things with non-fixed length lists of information. Okay, I think I'm going to go on break now. Before we actually look at the code, because there's a fair bit of code there, and I'll go on break and I'll come back and look at the code. So here's my break time slide. You were asking for more memes. Oh, I've accidentally put myself in the meme. I should be down here. Yes, as the smart one. Yeah, okay. So, linked lists are chained together, pointers, structs, and memory allocation. I'll show you the memory allocation when we come back. So a lot of the new techniques we've looked at, so a lot of the second half of the course, all ties into the idea of what linked lists are. So we start off by allocating memory so that we don't lose things, which means we can make things in a function, they stick around. We can allocate memory for structs, so we can allocate memory for more complex things. We can have structs with pointers that aim at the same kind of struct, which means we can chain together structs of the same type, which leads us to linked lists, and obviously I'm the biggest brain there, so I get to be, wait, where is it? There we go. Okay, let's take a quick break. It's about 12:05. I'll come back in, let's say around 10 past, or probably a bit sooner than that. And I'll go back through those slides that I just skipped over, and we'll look at the code that actually makes lists. We'll do a simple demo, and then we're going to launch into what is going to be a demo that follows us through several, probably 3 lectures at least, this lecture and 2 more after this, like all of next week. And we're going to build up an entire linked list demonstration that shows you all the basics of linked lists, because a lot of the things that we could do with linked lists are not trivial and require us to have a bit of an abstract understanding of what a linked list is and how it works. And so we're going to work through it, and we're going to actually spend a lot of time on it. Okay, let's go on break now. I'll be back soon. Alright, we're back. I came back a little bit earlier from my break, but I didn't want to like burn out my voice by talking lots, so I was just typing in chat. Music-wise, I definitely have a soft spot for what I would call the Bristol trip-hop music scene. So the Gorillas are actually like a second generation of that. You want to look at the first generation of the trip-hop scene in the UK. It's going to be Tricky, Portishead, Massive Attack, stuff like that. So that was for me. That was stuff that was really interesting back in the day. I mean, that sound is sort of, I guess you could say that sound went into the like sort of like that chill hop beats and stuff like that that people listen to nowadays. That YouTube channel for people like chill hop to study to has turned into like one of the biggest channels on YouTube. It's a bit like that, but it's much darker. Yeah, you can check them out if you want. More endorsements. They have nothing to endorse me with. They're old bands that don't even do stuff anymore. Anyway, okay, let's go back to the slides where I was going to talk about linked lists in code. So, this piece of code we've seen already. It's a struct for a node. So we are making our own variable type called struct node. And in the struct node, we have a pointer to whichever node is next in the list after it, and some kind of information that we're keeping track of, which is the data. The other thing that we're going to need to make a linked list is to have a pointer to the start of the list. So without knowing where our first node is, we're not going to be able to do anything. So let's have a look at how we set something like this up. So we could have a function that's going to add a node to a linked list. So this function is going to create a node, and it's going to return a pointer to the node that it has just created. So the output is give back a pointer to what you've just created and put these two things in. So put the data in and then make its next pointer equal to whatever we want to be next. So for the moment, we don't even have the structure built in for the linked list yet. We just know that we want something to be next. We can actually ignore, functionally most of the time, we can ignore this if statement. So this if statement says that if we run out of memory, we could exit the program. Although, if I remember correctly, last time we tried to malloc something when we were out of memory, the program was going to get killed by the operating system anyway. So we could actually leave this entire bit out. In fact, let's go back to code. I'm going to clear this. And I have a linked list example here that I'm going to open. I wonder if I actually already took that out. I'm going to take it out here and talk about it because it's a little bit easier to read if that's not there. So, create node here. I'm going to move this so that my pretty face is not in the way. Actually, I'm going to put myself back in the top right corner. It's better for the slides there, I think. Okay. So, this function here is going to create a node. It's been told it's going to return a pointer to the node that it creates. So in order to return a pointer to something, I need to have that pointer. So here's my pointer. My pointer here is just called n. I'm using a pretty simple variable name here because it's just a temporary thing that's not going to be reused. Maybe I should have called this node pointer or something like that to make it really specific as to what it is. In fact, let's do that. I mean, I'm not really expecting someone to get confused in 5 lines of code. I am expecting you to get confused in 5 lines of code because I'm showing you stuff here that you've never seen before, which is kind of confusing to begin with. But someone I'm expecting to read this, I wouldn't necessarily expect them to get confused, but I thought I'd change that name there anyway. Because it would just, you know, if you look at something and go, I'm not sure if people get confused or not, that means someone will get confused, and so you should change stuff. That's usually how I decide on my code style. Okay, so I've made my pointer here. It's not pointing at anything yet. I didn't even make it null. I just made it not pointing to anything. But then I assign it immediately to a memory allocation. So this is me going into memory and saying, I would like a piece of memory big enough to hold one of these struct nodes. Now, if I go up the top here, we have our struct node. This is exactly the same as in the slides. I put these in a different order here, but it doesn't matter, right? Because the ordering inside a struct doesn't make a difference, because every time that we're accessing the fields inside a struct, we're going to be doing it by their names. So since there is no like an array, the 0, the 1, the 2 or anything, there's no indexing, it doesn't matter which one goes first, as long as the stuff is in there. So I've got my information and I've got my pointer. So I've made a pointer to one of these structs that doesn't aim at anything yet until I create it. I create it by allocating memory. So I've grabbed a piece of memory big enough for one of these nodes, and malloc is always going to give me the address where it created something, and I'm going to store that in my node pointer. So at the moment, my node pointer is definitely aimed at this new piece of memory I've just created, which is exactly what I needed to make a node. The other thing that I'm going to want to do then is I'm going to fill out the information of this. So the same way that I've just created a variable, say I've just said integer I, and I haven't given it any values yet. So integer I needs a value, so we give it a number. Struct node here, which is at the end of node pointer, is going to need some values. So because it's a pointer, I use the pointy connector, the arrow, to find its data, and I say the data that's inside the node pointer is going to be the same as the data variable here that I was given. So note, these things are the same name, but this one is the one that's inside the node, because this one's at the end of the arrow, and this one, because it's not connected to any arrows or anything like that, is the variable that's in the function here. So you can actually have the same name for things so long as they're in different scopes, so they're inside their own sets of curly brackets. So this one here is this one. I mean, there's going to be many of these, but for the moment it's just one of these, and it's that one. And this next is this one. So what I'm doing is I'm taking the values that I was given when I created the function, so the values that I was given when the function was called, and I'm copying them into this new piece of memory. So I've created a new piece of memory with memory allocation. It's big enough to store everything that a node needs, and then I've created a pointer here that keeps track of where it is. Then I've gone in to the actual node itself, and I've copied in the values that I was given when I ran the function, and they go into this piece of memory because they're following into the memory, into the fields inside that memory. So when I finish this function, this pointer here is returned, and what it will do is it'll tell me you now have a node, and it has exactly what you told me to put in it. So this is the creation. You know what I'm going to do? I'm going to try to keep doing this visually. So when I call malloc, the following thing happens. I get a piece of memory, and then malloc is going to return the address of that piece of memory, which is this pointer. I'm going to take that address and I'm going to put that in the pointer that I had, which is called node pointer. Oh, now I wish, drawing with a mouse, I wish I had just called that N. Okay, node pointer aims at this. So that is these two lines. I've created a node pointer, and then I've allocated a piece of memory big enough for a node and I've aimed the pointer at it. I aim the pointer at it by storing this address here. So malloc is always going to tell me where something is. So now I have my node pointer pointed at the space that can be a node, and then I'm going to put the data and the next in that node. So come in here, I'm just going to split this up. So whatever data that I was given goes in, and whatever next that I was given goes in here. So they don't have any values necessarily, because this is just a function. Whatever values I put into the function are going to go in there. This next is a pointer as well. So it's going out into the world somewhere. I tried to make it squiggly because I don't know where it's going yet. It's going out into the world somewhere. We don't know where it's going yet. However I call that function is how that's going to be assigned. I'm going to trust that Michael is giving us all answers to things in there. Remember when I first showed you pointers and I said it was going to take a while before any of this sank in, and it was going to not necessarily happen the first time you saw it, and it was okay? This is the same thing. Linked list is just the next level of difficulty on top of pointers, and so don't worry too much if you don't entirely get what's going on at the coding level. But what we're going to try to do today, at least, is to get a decent idea about what's going on at the abstract level. So if I have pointers to things that allow me to access things, and the thing I'm accessing has some information and another pointer, it means that I can then put stuff on it. So it's nearly like I'm saying that, remember the houses? This is a treasure hunt. So a linked list is a treasure hunt. What I'm telling you is to go to one house. When you go to that house, there's some information in the house. That's the data. But the other information in the house is a little treasure map that says the next location that you need to get to is over here. So you follow that next pointer to go to another house. And then you go to that other house and you open up that house and you can get some information there, which could be some treasure, I guess. And then you get another map. And that map says the next house is over here, and then you go somewhere else. And then that's how a linked list ends up being built in memory with a whole bunch of these going around and allowing us to just move around and follow these pointers from one to the next. And then we can get from one piece to the next, and each one has its own little bit of data in there that we can work with. I don't know if that's helping or not. Yeah, we'll see. Yes, Cooper, a linked list is a treasure hunt. If we think of things like this, it's going to be a little bit easier for us to get a handle on them. Okay, I'm going to go back to my slides. So, actually no, that was the confusing thing in the slides that I made simpler by just removing part of it. So this create node here is going to be able to it's going to be able to make us one node, and it's going to put the data and the next in it. It's going to be made in memory somewhere, and then we're going to be given back a pointer to it. So what I'm going to do here, I'm actually going to delete everything in our main here. We're going to build this back up as we go. Don't worry, I'll give it to you with all the code in it. So if I have nothing else, I can create a node. So if I'm going to create a node, I can say I'm going to need a pointer to keep track of the node that gets created for me. I'm going to call this thing head. This is a keyword that we'll use a lot when we're talking about lists. The head is the first element in the list. So node pointer head is going to aim at the first node that I create. So I'm going to call that create node. And in that, I'm going to need to give it some information as well as the idea of what it's pointing at next. So the information I'm going to give it is just the number 1, and I'm going to say I need a pointer to another node to create this, except I don't have any other nodes. You see here, I've got the head and no other nodes, so I'm going to just say null to say that I'm creating a node that doesn't aim at anyone else yet. I can go back into this node here, now called head, and change what it aims at next if I want to. That will totally work. So this gives me a really, really basic linked list with only one item in it. So the one item in it is the number 1 stored in there, and there's no other items in the list because its next pointer is null, so it's not chaining on to anything else. So if we were to go here, this new one that I've just created, I'm just going to Control Z back through here. This is what we've got at the moment. This one's now head. I'm gonna change that. This is the pointer head that I've just created. I will also put the information in here that the number that I put in there was 1. Okay, so head points at this first thing that I've created, which has a 1 in it, and its next is null. Oh wait, I wasn't there, I was in my code. Right, so this is what my code is doing here. It's creating a start of a linked list that only has 1 element in it, and that has a 1 in it, and it's not pointing at anything else yet. James is asking me to go through the code that I was just working on and explain it line by line what it's doing. Okay, here. I'm assuming you're talking about create node. So even with my camera moved further away, you can still hear the fans going a little bit full on my computer here. There's not much I can do about that. Okay, so let's look at create node. First thing I do is I make a pointer. This pointer doesn't have a value yet, so this is a pointer floating somewhere. It's not aimed at anything yet. And then I call malloc. Malloc is a function that allows me to get a piece of memory. That's this thing in black here, is the piece of memory that gets created, and when it gets created it has nothing in it. So it's either empty space, it might all be zeros if your computer is really nice to you, but most of the time it won't even zero it out. It'll just have whatever random information was in our memory last time we used it. But it doesn't matter because we're not doing anything with it until we write some memory in there. We will then point this pointer at this piece of memory. So malloc, when it runs, will tell us where the memory is that it just created for us. Well, it didn't create, it just assigned to us, allocated even. I'll get there, I'll get the right word eventually. So malloc is memory allocation. So it allocates memory for a node and says it says here, this is the address of the node. We store that address in a node pointer. So this is the node pointer here, which we know is a pointer because we made it as a struct node pointer. So here's the variable type, struct node pointer, and the variable name is node pointer. So this pointer gets given the address of this piece of memory. So now I have access to that piece of memory because I have a pointer aimed at that piece of memory. The next thing I do now that I have access to that memory is I use the arrow to follow this pointer to the piece of memory and into the piece of memory to its data. So this gets me access to this field here where the data is, because I followed the pointer into the node and then into one of the fields of the node. That I'm going to write some information in there. The information I'm going to write in is whatever this function was given. So when I called it here, that was the number 1. So that means that that piece of memory, its number now becomes the number 1 that I was given. I then do the same thing for the pointer. So I follow this pointer into the node, and inside the node there's a next pointer. The next pointer is intended for us to see what node comes after it in the list. So this goes to a next pointer, and I assign that to whatever pointer I was given when I called the function. So when I call the function here, I gave it a null. So I said, just an empty pointer, please. I don't have anything I want to aim it at yet. Just leave it as empty. Then I'm going to put that into the next, which up here means this next is pointed at null. So null's not actually an object in our memory. I'm just writing null here to imply that this pointer is not going anywhere in particular. So it doesn't actually point at a thing called null. It's like pointing into non-space. So it's a bit of an abstract concept, but it's just not pointing into anything. Then we're going to return the node pointer, which means we're going to give the rest of my code the address of the location that we're in. So we're gonna tell people where this thing is, which means I can now assign the location of this to another pointer, like this pointer here, which is called head, which says this is where the start of my list is going to be. Okay. Yeah, everyone's laughing at how loud my computer is. Okay, I'm just looking at some of the questions. Sean saying malloc just allocates memory for the next node or the current node. Malloc just allocates memory. It does not know which node it is. So it just gives us a piece of memory, and it gives us the address of the memory. So if it gives us the address of the memory, then we can assign that to a pointer. So whether that's the current node or the next node depends on whether our pointers are lined up or not. So when we're creating a node, we're only working on one node here. We're not working on next or anything yet. We have a pointer to something that's next, but the thing that we're working on is the thing that's in this node pointer. So we create only one node here. And then we have a node pointer aimed at that node, and that node pointer gives us access to it and allows us to change the information inside it. So as is happening in this diagram, there's only one pointer. There's only one piece of memory here, which is the one node that we're creating. So we haven't created a next node yet. As it says here, it's null, so we're not aimed at anything else yet. Yes, as Sean is figuring out, you do need to malloc every node. So every node is going to have memory allocated to it. Someone is... Michael's reminding me, do I need to free this memory at some point? Yes, I will need to free this memory. If I was to run this code here with leak check, it would tell me that I have some memory somewhere that was created in this malloc that I haven't freed. So I wonder if... Oh yeah, let's just make sure. So if I free the head, this would then have no memory leaks in it. I'm not going to do that just yet, because there's more stuff that I'm going to do before we get there. I'm going to let Michael answer a whole bunch of these questions that are coming through right now. Yeah, so Peilong Lee is saying type of struct node pointer sounds really confusing. So yes, because a lot of the types that we started off with were these. An int. A variable type is something simple, it's a single word, and it doesn't have any other complications. But then we added stuff like pointers. So if I had a node point, if node was a type, I'm just going to move that there. a pointer is a type. And a pointer has two parts to it. One, the fact that it's a memory address, and the other is the thing that it aims at. So then we have a node pointer. But then if we have a struct is a two-word type. So now we have a type that is made up of three components. One is the struct that says this is a custom type that we've created. Then we have the name of the type we've created. Then we have the fact that it's a pointer to that type and not that type. So this is about as complex as it's going to get for us, is that we can have a pointer to a structure that we've created. And this is going to be the most complex type that we're going to be working with in COMP1511. It can get more complex than this. But for the moment, we need to be careful how we read types. So struct means that there's another word afterwards which says which struct it is, and we always need to look for whether there's a star there or not, which is whether it's a pointer. So once we get into the habit of how to read these, we'll be able to see the difference between an int and a pointer. So this is just a pointer. It happens to be pointing at a struct node. This is just an int. It stores 32 bits of number information. Jeremy's also saying, should we free it? Yes, we should free it. So after we're finished using it, we should free it. The question was, should we free it after we declare it or after we finish using it? So remember what freeing does. Freeing is going to say we're not using it anymore, and we free the memory to go back to the system. So if we had intentions to continue using this thing afterwards and we freed it, then we wouldn't have access to it. So once we free it, it's gone. So for example, if I do this, let's just write free head. So this is going to say that whatever the head pointer is pointing at, which is the node, because that pointer is pointing at this memory allocation, we're going to give it back. So here I could say head data equals 100. So I could change it to 100. And here I can say head data is equal to 200. If I try to run this code, actually let's run it. I think am I set up to run? Yeah, I am set up to run this. Okay. DCC linked list demo. I'm gonna run that. Oh, malloc use after free. So access to memory that has already been freed. So after I free it, it is no longer available to me. I can't use it anymore. So here it was at this line here that the problem had happened. So this should only happen when you're finished with it. So free should only happen when there's no other things that you want to do with that piece of memory. So if you have something else you want to do with that piece of memory, it should have happened before you freed it. And likewise, you shouldn't free something until you're finished with it entirely. So I hope that gives you a little bit of information about the difference between when you would free something. So here I can make some changes and then free it. William's saying, if I have multiple heads, so multiple pointers aimed at different nodes, would I have to free them? Yes, I would. The other thing is, if I have multiple memory allocations, let me just go back to my slides, like this, I would need to free each of these nodes that have been created, because each one of these is a separate memory allocation. We're not going to look at that today, because we don't have enough time to look at that today. I'm just going to do the basics of just building up a list. Actually, where am I in my slides? Alright, we have a function to add a node. Let's build a list. Actually, I'm not going to do it exactly like this, but we'll do it a little bit like this. I'm going to do it so it kind of goes in order. So what I can do now, so I've got the head of the list, which means I know where the start of the list is. I have an end of the list, which is a null pointer that's off the end of things, which is here, null pointer. But what if I want to add another element to this list? So what if I don't want this thing aiming at null? I want it to aim at another node. So I'm going to call create node. I'm actually going off script here and I'm changing the way that I did this, but that's okay. So I want to create a new node here. And I want to put a 2 in this node. And it's going to have a next pointer aiming to null. I'm just going to make a null off in the corner here so I don't have to keep rewriting null. And then I want this next pointer to be aiming at this new node. So let's look at the code that makes this work. So if I call create node with a 2 and a null, what this is going to do, I need to actually call it by its correct name. What this is going to do is it's going to allocate memory for a new node. So allocate memory for a new node, and it's going to give me back a pointer to that node. So if it's going to give me back a pointer to that node, and I have my head node being my first node here, and I want its next pointer to aim at the second node that I created, then I need to change its next pointer, as I did a second ago, from pointing to null to now pointing at this new one that's been created. So what I can do is I can say head next equals create node here. So this is going to now allow me to add a node that's after the head, and so the head's next is no longer going to be null, it's going to be aimed at this one. I have some limitations here, and I'm not going to go too deep into this because in order to create longer lists, I need to decide exactly how I'm going to add nodes to the lists. I'm not going to talk about that today because I think that there's a limit to how much I want to melt your brains in one go. And so I'm going to say that this is the start of how I'm going to create lists, because as you can see already, it's actually pretty hard to add a third element to this list. I could squeeze a third element in the beginning by aiming the head at it, and it's next at what used to be the head, and just fiddly stuff like that, but I'm just going to leave it as these 2 nodes for now. The other thing I wanted to look at, I do have this inverted way of creating a list where we could put all 5 of these here, and we do it actually backwards by having your head pointer and squeezing a new thing in the front, and then moving the rest of them along, squeezing a new thing at the front, moving them along, and that. So you can look at that if you need, but I wanted to at least have a quick look at what it's like to loop through a linked list. So we, up until now, had 2 kinds of loops we were using. One was loop a specific number of times, and the other was loop until a certain condition changed. So with a linked list, we're going to use the second type, which is when a certain condition is triggered, in a sense, we're going to stop looping. And that thing is going to say, when the node we're looking at is null, we are going to stop looping. So what we're going to do, and I'm going to go back across to my code here, is have a look at this piece of code here, which says loop through a list of nodes, printing out the information that is in those list of nodes. So the stopping case is n is not equal to null. I've got some diagrams I'm going to show you for that. And the way that we move through our nodes is to say we have a node pointer, this is the node pointer n, and that node pointer is going to move along the list. Let me show you the diagram. Actually, it's better to do the diagrams in the code. Okay, so here we have our list. It's exactly the same as the list I just created, which only has 2 nodes and some information. So in order to loop through this list, I'm going to start with a copy of the head. So when I run a function, I'm going to get a pointer here which is aimed at the same thing that head is aimed at. So if a pointer is a copy of another pointer, they can be in different places, but what they're doing is they're aiming at the same thing. So they're both aiming at the first node in the list, which is the head. So we're going to start here and then we're going to loop through. So the first thing we're going to do is we're going to grab that data and print it out, which is here. So print out the data and the node that we're currently looking at. And then what we can do is after we're finished with this, we then take that pointer and that pointer becomes a copy of the next pointer that was in that node. So the next pointer was in that node was aimed at the next node in the list. And so our pointer just moves to the next one. Also from your perspective, it moves. So first it was looking at the first element and then it says, okay, I'm done with you. Tell me who's next. And it shows you the treasure map and says, this other one is next. So you go, okay, now we move to that location. So this pointer is actually moving between the locations in memory where each of the nodes in the list are. So it goes from one and it uses its map, its treasure map, its next, to say, okay, where is the next one that I'm going to? And it moves its pointer there. And then it looks at that one, does whatever processing it has, and then it moves on. So when it moves on, it will keep doing this to all of the nodes in the list until at some point following all these next pointers, one of the next pointers at the very end of the list is going to be equal to null. So if it's equal to null, I will then end up pointing at null. The pointer still exists, right? The pointer is still moving around, but eventually it will get to null, and then the while loop's question that says keep running the loop until you are null. So until the pointer is aimed at null, keep running the loop. And so we would have kept running the loop, but then we ended up pointing at null, and when we were pointing at null, we are now in a situation where we know that we've gone through all of the elements in the list, and we've reached the end of the list because there is no more node that we can point at now. We're pointed at null. And that's going to end the while loop there. Oops, let's not go to that. I have an example that I'm going to do, but I think I'm going to start that one next week rather than now. So let's go back to my code here and look at this while loop. So we start with a pointer, and this pointer, I've got like old habits with C++ where we would put the star usually on the name of the struct there, and I leave them in sometimes by accident. Okay, so when we do print data, we are given a pointer to a node. If that pointer is not null, we go into the while loop, we print something out, and then this is like our I++. Remember I++ with an array would go from one array element to the next, because the index was just going up by one. So that would move us from one element to the next. Now, in order to move us from one element to the next, we take our pointer n, and then we say n is no longer where it was before. We want n to now be the next. So for example, if I start off with a copy of the head, my n is here, and it's aimed at this one. If I then say n is equal to n's next, so n's next, this is n, and I go in here and I look at the next, its next is here. So this memory location is n next. So if I was to say n equals n next, n would no longer be pointed here, it would follow the next, and it would say I am now pointed over here. I can tell my computer is getting super loud right now. Yeah. So this then moves this pointer along, and then I could follow this next to try to find the next element in the list. And what it would get is this null here. So this n is going to just move its way through the elements of the list by saying, who's next after you? So this one says, this other one's next after me, go there. So you go there, and this one says, there's actually nothing after me. So you now go to null instead of anything, and then that's how you know where this thing stops. So like every list, the way that we were working with lists previously is that we know how it's going to stop. So we know it stops if the pointer ends up being null. That means I've moved off the end of the list. That's exactly the same way as saying is the index less than the length? Because once the index is equal to the length, we've gone off the end of the list. So it's the same kind of thing of going off the end of an array. Going off the end of the linked list is just signified in a different way by the null pointer. We do something inside the list, and then we move to the next element of the list. So this basic looping through a linked list is something that we're going to be doing a fair bit. So this is like when I first taught you to loop through an array, where it was like index 0 as the start of the array, add 1 each time, and it moves through the array. This is the same, where the head pointer here is the start of the array. And then we're going to go through, and each time we want to move from one element to the next, we change n from being where it is now to being where the next is. So it follows the next pointer to find the next one, and then it stops when we've gone off the end of the list and the n is null. So let's have a look at this here. So I've got to do it before I free anything. I have a function called print data, and it is going to take in a pointer to a node, and so we want to give it the pointer to the first node, which is head there. And so if we give it the head, it should print out 1 first and then 2 second. And then because 2 was pointed at null, it should end there. The reason why this null doesn't mean anything anymore is because we've changed what heads next is in this next line to point at the second one. So after I've done these 2 lines, my structure in memory looks like this, not including this bit. So I'm just going to remove that for now. Oh, look at my precision there. Okay. So, yep. So this is my structure in memory, and I'm just going to be moving along that and printing things out. Let's have a look at that running. I'm going to compile that again, and then I'm going to run it. Alright, so we printed out a 1 and then a 2, which means what we did was, at the beginning we called create node, and we assigned the head to that create node. That allocated memory for a single node with 1 in it. Then we said your next was null, but we want to change your next to aim at another node. So we find the head's next and we say you're no longer pointed at null, now you're pointed at the second node we've created. So we create the second node, it gets its memory allocated, and then it gets given a 2 and it gets given a null to say now you're the end of the list. Previously the 1 was the end of the list, but then we changed its next pointer to point at another node, so now node 2 is the end of the list, with its pointer pointed at null, and since we didn't add anything after that, 2 remains the end of the list. Then we call print data. Print data starts with the head, because it was given the head as where it started, and it goes in and it says the head is not null. The head is pointing at a node, and so we can print out the data in that node, and then n becomes the next of the head. So it moves from this first one to this second one here, and it goes through the loop and it comes back again. The second one is not null, so it can print out the information that's in the second one, and then it follows the second one's next, and then it becomes null. It loops again, and it says we are no longer passing this case because the pointer that we're using has become null, because it's gone off the end of the second one and it's now aiming at the null here. In which case this print data will finish and we'll get here. At the moment we're freeing the head, but we are not freeing the head next here. So we have a problem there that we haven't quite finished. I'm not going to talk about that yet. Freeing is more complicated and we will get to that soon. So now we have the capability to have these linked lists and to be able to move through them. Let's see if there are any questions here. There's quite a few questions happening. Oh, Tom has to go set up his tute. If you look in the course notices on the course webpage, I don't think I've got it open at the moment. I think my most recent notice, as well as an earlier one, has a remote working survey, which is just some information we'd like to get about how people are going working from home and whether people have reliable enough internet connections to continue working from home. So if you could go to that survey and fill that out, that would be really helpful. I fully understand that some people are not here in the live stream because of their working from home conditions, and that's something that we have to that we're trying to make sure that we support. So if you're watching this after the fact, please go and fill out that survey. That will be really handy for everyone. Michael's saying he calls the arrow a stab. A lot of people call it that, and I like that because the stab is reminding you that it's sharp, and pointers are sharp points, so you only use the stab or the arrow on pointers. Okay, couple of questions. Griffin's asking, do you have to free all the nodes or just the head? You have to free everything. So, for example, let's compile this with leak check. And I'll run it again. It runs the same as last time, but now it's telling me free not called for memory allocated with malloc in function create node in linklist.c at line 30. Line 30 is here. We kind of knew it was going to be here because there's only one place in this piece of code where I'm allocating memory. So malloc here is being used at some point. So it's one of these two calls. We don't know which one. Leak check can't tell us that much. It can only tell us that there is memory we haven't freed. We have freed the head, but we know we haven't freed the head next. So we know that there's an issue there and there is a memory leak because every time we called malloc, we have to free it. I'm not going to talk about freeing just yet because freeing a list involves going through the list and freeing them one at a time. So you have to go through the list similarly to how we loop through the list here and we free it. I will look at that later when we get into specific examples. William, yes, this is the hardest lecture. This is definitely the hardest lecture because this is piecing together everything. So it's like everything that we've learned so far pieces together in this, and the kind of abstract thinking of pointers comes in here. Don't worry though. This is definitely not the last time I'm going to talk about this. I'm going to keep talking about how these things work. My advice for understanding this is draw pictures. It's nearly always going to be these kinds of pictures that are going to remind us of how these things are connected together as we're building them in code. So I nearly always draw pictures when I'm building data structures like this. I'm just looking at if there's any other questions. Jeremy's asking an interesting question. Why don't we free ints and arrays and other things that are stored in memory? If you go back and look at the slides that I was going through yesterday, anything that's created inside curly brackets, so it's created as a variable that is contained inside curly brackets, will always get cleaned up itself when the curly brackets finish. The only reason we have to use free, actually let me just, where is it? No, not in there. Hang on. I don't want to open it on the screen that has that you can see because it's got stuff like assignments and stuff in there. So alright, here's my memory allocation lecture. Oh, also we have hit 1 p.m. so if you need to go to a tutorial now, feel free to head off to the tutorial. I'm just going to answer some questions here while we are still here. Okay. So, where are we? Memory. Yeah. Okay. So, here we have our memory. We have our main function and a function that's called by main, and the variables are declared inside this function. When the function ends, the memory disappears. So this memory is cleaned up automatically. The difference with malloc is assigned memory that is not contained in a function. So when we use malloc to memory allocate something, it gets put outside the functions. If it's outside the functions, it's not going to get cleaned up automatically by the curly brackets. So it is in what we call a scope that's outside of the functions. The functions still have access to it if they hold on to the pointers. So if each of these functions, the main function, the other function, have a pointer to this memory, they can still make changes to it, and they can still use it, and they can also still free it. So this memory, the function ends, and that memory is still being held. Even the main function ends, and this memory is still somewhere. Having said that, when the program completely finishes, my computer will go back through everything we've used and clean up the memory. So, in a sense, everything kind of gets freed when the program finishes, but it's very, very bad to rely on that. We want to make sure that we clean up after ourselves, not just expect things to just magically get cleaned up after we're done with it. That's a life lesson right there. Clean your room. Okay. I think Michael was answering that question. Michael and Abraham were both answering that question. And I think Abraham answered it in exactly the same way that I was showing here. William is asking about why I'm using a struct in the main function when create node is a struct already. Let's have a closer look at what that question actually is. Here. So, create node is not a struct. Create node is a function. We know that because it's got these normal brackets there and has some inputs. It is a function of type struct node pointer. So, create node will return a pointer to a struct. So it will return the location of a struct. That does not make it a struct, but it means that if I want to store the result of this function somewhere, the thing that I'm storing it in should be the same type as the function. So create node is going to return a function, a struct node pointer. So it's going to return a pointer to a node. So if I want to hang on to the return, so the information that I was given for it, I need something that stores the same type of information. So I've made a pointer to a node here called head, has no information until I run create node and I take this pointer and I put it in head. What that does is when it creates this piece of memory here, I can then assign the head pointer to that piece of memory. So now I have control of that piece of memory and I have access to it. I hope that's enough of an answer to answer your question. Oh, there's talk of global variables. We're not going to use global variables. They're very dangerous. We can't control how they're used if we have global variables, which means people can write into them by accident. Other parts of our code can write into them by accident. Much prefer containing things in C&H files. So instead of there being globals, there are things that you can access, but they're protected. That's the danger with using globals. Jeremy's asking if we have to malloc the pointer. We don't have to malloc the pointer, but we get given a pointer when we malloc, which is exactly what Abraham is saying there. Yeah, cool. Hyundong Xiao is asking if we write node star, so the difference between this. And this. C does not have a difference there. it's much easier to read it if we put the star on the variable itself. And the reason why we might do something like that, I'll show you something that's a bit interesting about this. So let's say I have some integers. I have an integer and I'm listing multiple at the same time. You can do this. You can list multiple at the same time. If I put a star here, what this looks like now is I'm making 3 integer pointers, right? So it looks like I'm making of type integer pointer, I, j, and k, that are all integer pointers. What actually happens is I is an integer pointer, and j and k are normal integers, which is why we move it to here, so this looks more like what's actually happening. The int pointer here this is a pointer, and these are not pointers. We want these to be pointers. If I remember correctly, correct me if I'm wrong, although Tom I think has already left. If I wanted multiple integer pointers, it would have to look like this. So that's why the star goes onto the right next to the variable name, to make sure that this kind of confusion doesn't happen. I mean, it's really rare that we would do something like this. I would nearly consider this to be bad style, because this is going to confuse the hell out of people. I'm going to get rid of it, because I think it's probably confusing the hell out of people right now. Yeah, so Cooper, that's the reason why we do it. And yes, I know for a lot of people, including myself, because in C++ the convention's more like this. Because it would be like this. It does seem to make more sense because you want the type to be all bundled together. But because of that other example, we do it like this to stop confusion in other cases where we might declare more than one. Yeah, so Abraham, I do understand, and Cooper as well, that it could be more more intuitive to put the star here, saying that this is a thing of type pointer. And we had someone else, I think Peilong Lee earlier was saying that this is very confusing. So yeah, I do understand the confusion, and would probably be less confusing if the star was attached here, but it could lead to other mistakes later on. So it's a bit of back and forth, but we're going to try to do it this way, because if we're going to have mistakes and confusion and things, it's better for us to have things be factually correct all the time, and then need to sort of get over the confusion a little, but always have it factually correct. Because if it's not, then we could end up in a situation where people won't know why things are going wrong in the future if they start to declare multiple pointers in a row and then wonder why some of them aren't actually being pointers. So that's why we're going to use this notation, and remember that this is the type of this variable. Okay, let's just see if there are any final questions. If there aren't any final questions, I'll wrap it up there, because we're a little bit over time. And I think you can hear it already that my voice is a little bit sore after today. It's always like after the second lecture in 2 days, my voice always gets a bit sore. Alrighty, so I think that we are done with the questions for now. We're going to wrap it up there. We're going to be doing some introductory linked list building in the Tutes and Labs next week. Next week's lectures, we're also going to go through and start doing a larger worked example and look at things like proper adding to lists, removing from lists, how do we free the entire list, and all this other stuff that's going to be happening. We'll probably end up spending the whole of the next week on that, I think. Cool. All right. Have a good day, everyone, and I will see you next week.